Welcome to lesson 5.4, use medians and altitudes. So last few lessons, we've looked at different types of bisectors of triangles, whether they're angle bisectors or perpendicular bisectors. Now in this lesson, we're going to look at two other segment pieces known as medians and altitudes. So to start with, a median of a triangle. So a median of a triangle is a segment from a vertex, meaning a corner, to the midpoint of the opposite side. So there are three medians within triangles, and those medians are all concurrent, meaning they cross at the same point. And in this case, the point of concurrency for the medians is called the centroid. So we've already looked at incenter and circumcenter. Now we have a centroid. So the centroid is the point where the three medians meet. And a median goes vertex to midpoint of the opposite side. So for example here, B being a vertex to F, the midpoint of the opposite side. So BF would be a median. Same with CD and same with AE. So those are three medians. So then we have theorem 5.8 about the concurrency of medians of a triangle. And it says the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So what that means is if we look at the whole median AE, that rule tells us that from the vertex to that point of concurrency, the centroid, AP is 2/3 of the whole segment, and PE would be 1/3. So what that means is AP is 2/3 the whole median AE. So AE times 2/3 would give us AP. BF, this whole median here, multiplied by 2/3 would give us the distance BP. And CD, this whole median, multiplied by 2/3 would give us the distance of CP. So looking at that theorem and our example here, it says in triangle RST, Q is the centroid, and the distance of SQ is 8. Find QW and SW. So what we know is SW, that whole median, multiplied by 2/3 would equal SQ. So if SQ is 8, 8 equals 2/3 multiplied by whatever SW is. So to get SW, we would do 8 divided by the 2/3, and that whole median length, SW, is 12. And then we know SW, the whole segment, minus SQ will leave us with the length of QW. So SW being 12 minus SQ, which is 8, gives us the distance of QW being 4. And then we go down to example 2. Example 2 says the vertices of triangle FGH are, F is at 2, 5, G at 4, 9, and H at 6, 1. So the first thing you want to do is sketch that triangle. F here, G here, H here. And apologies that G goes off your graph a little bit. Just do the best to approximate the height. Then they want us to find the coordinates of the centroid P. So trying to figure out where the centroid P is for that triangle. So we're going to first sketch FGH. Then the second thing we're going to do is use the midpoint formula to find the midpoint of side FH. So we're going to use F and H and put it into the midpoint formula. So add the X values, divide by 2, add the Y values, divide by 2. So that tells me the midpoint of that segment is at 4, 3. So I just labeled that K. So the midpoint we had to figure out so we could draw in a median from G to K. So you sketch that median GK. Then what do we know? Well, we know the centroid is 2/3 of that distance of G to K. So starting at G going to K, the centroid P is 2/3 of the way to K. So if G to K, that segment was 6 units long, we multiply that by 2/3, and that tells us our centroid was 4 units away from G, the vertex. So we would go down 4 units along that median to find point P. So 4 units down from G puts us at the point 4, 5, which is for P, which would be the coordinates of our centroid. So the idea for this is you'd sketch your triangle, you'd find the midpoint of one side, and you'd draw that median, and then you'd figure out how long the median is and multiply it by 2/3 to figure out how far from the vertex is your centroid. So again, everything goes back to this idea that the centroid is 2/3 of the whole median length. And then we get to our other segment for this lesson, which is an altitude. So medians go vertex to midpoint. An altitude of a triangle is perpendicular. So it's the perpendicular segment from a vertex to the opposite side or to a line that contains the opposite side. So what they mean by that is here, if we're looking at triangle PQR, from Q to PR, if it meets PR at a 90-degree angle or perpendicular, then that segment right here would be the altitude. And it would be the altitude from Q to side PR. Well, what if Q is up here, and this is our triangle? How do we draw the altitude? You would extend side PR so that we can have that perpendicular going up to Q. So this piece in red is not part of our original triangle, but we have to extend the line that PR is on to draw the altitude. So it goes from a vertex to meeting the opposite side at 90 degrees. So then, concurrency of altitudes of a triangle. Theorem 5.9. So if we're dealing with just altitudes, yet again, those points are concurrent, meaning they cross at a single point. So in this case, all of our altitudes would meet here at point A. So the lines AF, BE, and CD, those are all labeled wrong now that I look at it. Definitely labeled wrong. That should be, if we're labeling these as altitudes, it would be GF, it would be BD, and it would be CE. So their point labeling here was wrong. It should go GF, because that altitude goes from G down to F. It should go B to D, that altitude goes B all the way to D, and then C to E, and those all meet at point A here. Oh, never mind. I'm an idiot. Let's rephrase that. Apologies. I thought the original triangle was CGB. Original triangle is ABC. So my apologies. So the original triangle is ABC. So they are actually right. Our altitudes would be from A to F. Then the altitude for C to the opposite side is we'd have to extend the line that BA is on. So our altitude would be CD. And then for finding the median or the altitude going from C to side AB, that would be C going over here across that way. So we would end up with CD, we would end up with BE, and we'd end up with AF. So our three altitudes for triangle ABC all meet at point G. Now, the point that our three altitudes meet at, so going vertex to 90 degrees or perpendicular with the opposite side, the three altitudes intersect at a special point as well called the orthocenter. So now we have a circumcenter, an incenter, a centroid from up here, and then we have our altitude piece, which is an orthocenter. So to find the orthocenter P in an acute, a right, and an obtuse triangle. So if we were to draw in the altitudes, and I'll make a brief video or post a brief video showing you how to easily draw in altitudes for triangles, we would see if we have an acute triangle, our orthocenter, where the altitudes meet, is on the interior. If we have a right triangle, the altitudes meet at a point on the triangle. In this case, point P in the bottom left corner. And if we have an obtuse triangle, like the pink triangle here, then your orthocenter, the three altitudes, end up meeting outside of the triangle. And again, these are just some quick sketches. I'll show you a video showing you how to create an orthocenter and draw in altitudes. And then we get to our final couple ideas. So in these final few ideas, it says triangle PQR is an isosceles triangle. So that means two sides are congruent. And segment OQ is an altitude. So OQ here is an altitude. What else do we know about OQ? What are the coordinates of P? So we're trying to answer two things. What do we know about OQ? And what are the coordinates of P? So in this case, saying that OQ was an altitude, because PQR is isosceles, it ends up happening that OQ is also a perpendicular bisector of PR, meaning it meets segment PR at 90 degrees and cuts it into two equal pieces. And in this special case, again, because it's isosceles, we also know that OQ is an angle bisector of PQR, meaning angle PQO and RQO are equal or congruent. And lastly, because again, it's a special case isosceles, we also could state that OQ would be the median. So then in this case, to find the coordinate of P, if O is at 0, 0, and R is at a positive H0, we know the distance OR is equal to PO. So we would be going left H rather than right H. So our X value is a negative H, and we're not going up or down at all, so that would be a 0. And then our last piece. In figure P is the centroid of XYZ. So P here is the centroid of triangle XYZ. And then they give us some info. They tell us the distance from Y to P is 12. They tell us this piece, LX, is 15. And they tell us LZ, going all the way across here, is 18. So find the length of LY. LY here is equal to LX because if P is the centroid, we know LZ meets side XY at its midpoint. So the distance X to L would equal the distance Y to L. So that's also 15. Find the length of YN. So YN is this whole piece here, our whole median. What we know then is that PY is 2/3 of YN. So PY equals 2/3 times YN. Well, if we know that this piece here was 12, we would divide it by the 2/3, which is the same as multiplying by 3/2. So if 12 is 2/3 of the whole segment YN, 12 divided by 2/3 gives us 18. So YN is 18 units. And then to find the distance of LP. L to P, right here, is 1/3 of LZ. Because from Z to P, that's 2/3 of that median. So LZ would be 1/3 of that whole piece. So LP is 1/3 of LZ. So 1/3 of 18 would tell us that the distance L to P is 6. If we wanted to find the distance P to Z, that would be 2/3. So that would have been 12. So now we have a lot of different points of concurrency and segment types to keep in mind. So you want to make sure that you have good notes for these last few units, and you want to make sure that you have them handy for any upcoming assessments so you don't confuse our 4 different points of concurrency and the theorems that go with those points of concurrency. And again, I'll create or I will attach a second short video showing you the easy way to draw in altitudes for triangles.